we are now going to be able to bridge together the ideas of linear systems with matrices. Before we do so, just a couple quick reminders. So first of all, that of an identity matrix. So when we're dealing with an identity matrix, we're usually assuming it's the multiplicative identity matrix, and that's going to be the matrix that is always going to be a square, so that means that its number of rows is the same as its number of columns, that contains the numbers 1 throughout the entire main diagonal, and then zeros everywhere else. And so property-wise, what we'll see is, if you look at the calculator, I have the left-hand side right there. If I take matrix B, which is just a random 3 by 3 matrix, and then if I multiply it with what I've defined as D, which if you look at D is the identity matrix, that's the 3 by 3 one, then I put B times D, and B times D actually just equals B. So multiplying by an identity matrix is sort of just kind of like multiplying by 1. You just get the same answer. It does work the other way too with identity matrices, that D times B also does just give you B, but most other cases matrix multiplication is not commutative. And another quick little reminder right here in terms of inverse matrices. So we did not discuss formulaically being able to find inverses for matrices that are like 3 by 3s and 4 by 4s, etc. We only discussed it for a 2 by 2. So that's given here as just a reminder. So if you're finding the inverse of matrix A there, then you would formulaically use 1 divided by the determinant of A. That's what the bars around the A is indicating there. So to be able to find what that determinant is, you have to take the numbers in the main diagonal, find their product, and then the other product would be negative 20, and you subtract, and then you'd end up adding 20 to negative 8, which gives you a positive 12 therefore. So that's the scalar that's going to multiply to this matrix. You're going to have to switch the negative 1 and the 8 around, the numbers in the main diagonal, and the other numbers stay exactly where they are. And then we can just multiply that 1/12 to all of the entries there. And then in reducing all the fractions as well, we end up with the following, which is the inverse matrix of A. So the power of finding an inverse matrix is that then when you take the matrix A and you multiply it with its inverse, it'll actually like cancel out the matrices and give you the identity matrix as the answer. And the same thing works the other way as well, that if you do the inverse of A times A, then you'll still get the identity matrix there as well. So we can find that formulaically, but more efficiently, of course, we can use technology to be able to do so as well. So if you're using a calculator, you could find an inverse matrix just by using that. So I'm going to type in these values that we have for t right here, and then we'll enter that. Beautiful. So I guess I define that A on Desmos. So if you were to find the inverse of that, you just need to hit the name of the matrix, and then if you want to find the inverse, there's a little button there that has the -1 superscript, and that'll give you the inverse. Actually turns out very nice right there. So the T inverse, we would call that, be -1, 2, 1/2, and -3/2. Excellent. All right. So now getting into new territory here for us. We're going to, like I said, be connecting matrices to linear systems. So I want to start by taking a look at matrix equations. So clearly an equation is going to have an equal sign, right? So if we're dealing with a matrix equation, now you actually have matrices involved, of course. So when we're solving equations, now think that this is just like a real number problem. And if we're solving ax equals b for x, then we're wanting to find what the value of x is. So when I say we're thinking of this in terms of real numbers, like the a and the b, as well as the x should be real numbers. So for example, if you had this problem, like 6x is equal to 22, and you were to solve that problem, that's the sort of thing we're talking about right now. So of course to solve that, right, like you normally would probably think like, okay, we can divide by 6 on both sides, and then we get our answer for x, which has to be 11/3, right? If we were to try to do that with matrix equations, so in this sort of a scenario, if I have a matrix A multiplying with the matrix X and equals another matrix B, so there's A, there's X, and it equals B, right? So if you were trying to solve to get the X alone, you might think, oh, could we just divide by matrix A there, and then that would like cancel those out? And you can't, because there is no operation of division with matrices. you can only add, subtract, and multiply with matrices. There is no division operation with matrices. So then if we were to try to solve this equation and try to get x alone, right, we want to be able to get rid of the a somehow, but like, how do we do so? And so if we go back to this real number problem right here, we could also approach 6x equals 22 and get rid of this 6 by multiplying, but multiplying by the inverse, right? Because if you multiply by 1/6, then you can do 1/6 times 6, which is 1, and give you just the x alone. And then if you multiply that by 1/6, you get 22/6, which reduces to 11/3. So you can always multiply by the inverse, right, to undo multiplication. And so because we know how to multiply with matrices, right, then sometimes multiplying by inverses will allow you to cancel things out. And that's exactly what we want to be able to do here to solve this for x. So if I take this equation, I can do something to both sides of it. And if I want to get rid of that matrix A right there, then what I need to do is I need to multiply by the inverse of A, right? Now it's really, really critical and important that when I multiply by the inverse of A, that I do multiply with the inverse here right in front of the equation, because I need A inverse and A to be right next to each other. Because otherwise, if I had decided to put the A inverse after the x, then that's not going to be helpful for us, because as we've discussed, matrix multiplication is not commutative, and so if you put the A inverse over there, like, it's just going to be a mess, and you're not going to be canceling out the matrices because they're not next to each other. So it's really important that I multiply by A inverse there on the left, and then you have to do the same thing to the right side. You can't just multiply the A inverse to any side. Like, it has to come before the B matrix, because you made the A inverse come before the A times x on the other side. So what's going to happen right there then, because we'll go from left to right, is then A inverse times A is going to equal I. And so then you'll have I times x equals A inverse times B. But then we know that right there, anything times the identity matrix is going to equal just the same matrix. So you just get x. And now we've actually isolated x, as we've been asked to do here to solve for x. And so to solve for x, then we just need to take the inverse of that A matrix and multiply it with the B matrix, and that will give us exactly what x needs to be to solve that particular equation. All right, so it's a little bit more general because we haven't really done this exactly with examples, but that's exactly what we're going to do right now through example. So it says here to solve the matrix equation, which is of the form AX equals B for the 2 by 2 matrix X. And more simply, just solve for x. So if I wanted to solve for x right here, what I need to undo is I need to undo this multiplication that in front of it is this matrix 5, 7, 4, 3. So really what you'll want to do is then just in front of the 5, 7, 4, 3, you'll want to do the inverse of whatever 5, 7, 4, 3 is. And then similarly, that means that right there, if I can kind of sneak it in front right there, draw an arrow to it, whatever the 5743's inverse is, I need to multiply to the other side. So, like, without even really doing this in a calculator, we know that that times that is going to equal the identity matrix. So you're going to get I times x, and then on the other side, we're going to get whatever the inverse of 5743 is, and then multiplied with negative 3014. So I'll erase the I right there since we know it's just going to be x. So that's going to give us an answer. That's a defined matrix multiplication. So to find what that answer is, then we'll want to go into probably a calculator to do this fastest, or do this the most quickly as we can. So here, let me just clear everything up. So let me define a new matrix here as A, and I'll define it as the 5, 7, 4, 3 matrix, and then we'll define another matrix here. That will be the matrix that I guess we called B, negative 3, 0, 1, and 4. And so basically right here, we just want to take A inverse and times it with B, and that should equal what our matrix X is. So on the calculator here, if I just do A, and then the inverse of A, and then I type in B, then that's going to be what A inverse times B is. We don't get the nicest of answers, so I'm going to hit that little button that'll turn everything to fractions. So it seems then that X should be the matrix, all those fractions there. and that solves it for x. So it's kind of what we're looking for. So to make sense of what's really happening here, the original equation was just saying that if we have 5, 7, 4, 3, that matrix, now if we times it with x, which we're proposing is 16 thirteenths, 28 thirteenths, negative 17 thirteenths, and negative 20 thirteenths, then that is going to be equal to, when we multiply that all the way out, negative 3, 0, 1, 4 as a matrix. So if you do work your way through that matrix multiplication process and the pairwise multiplying, all that sort of stuff, then you'll verify that it does actually work.